Hello everyone, welcome to a new lecture. Today we're going to discuss how to train models. So far we have solved different problems in regression settings, classification problems, but we haven't discussed how actually those algorithms works. Those libraries that we're using, mainly scikit-learn, and we're using different methods like to solve linear regression problems or using different algorithms. So today let's discuss some basic algorithms that are very useful when you're training a model. Okay, so the main idea of training a model is to estimate the parameters that the model requires to make a prediction. And of course, we want to minimize the prediction error. That will be our objective while trying to estimate the model parameters. There are different approaches. So in this video, we're going to talk about normal equation, which is mainly like linear algebra, and is like the typical solution for linear regression problems. We will talk about also gradient descent algorithms. These are like a very general and flexible algorithm in optimization. And of course, we're going to mention regularization and the importance of this concept. Okay, so the training is important because the method that we use will affect the accuracy, the efficiency, and the ability to scale if we're increasing, let's say, the number of observations, like, I don't know, 200 of thousands or even millions of observations, then it matters which algorithm you're using to train your model. Okay, so let's get started with the basics, with the linear regression. So in the linear regression, the idea is that this is just a simple linear regression. So you want to predict a y variable with an x variable, right? And you have a multiple linear regression when there are at least two independent variables, x1 and x2. But in general, of course, you will have x1, x2 up to xk. You have multiple features to predict the y variable. So the linear regression, the assumption is that there is a linear relationship between x and y, right? So you can fit the data with a straight line. This is in the case where there's only one feature, and this is the structure that it has in general. So y hat, we use the notation of hat. You will see the hat every time we refer to a prediction. So if you see y, like in the plot, y means the real value. So that's the value that we have in our data set. That's a measurement or an observed value in real life. And when you see a hat, like y hat, this means the prediction, right? That's what our model is saying. So every single point in the line that we have here, the line that I just added, that will be y hat, right? Because that's like my prediction using a model. Okay, so the distance between each observation, each real value to the line, that's like what we're finding there is like y hat minus y. That's the error. That's the error or the residual, right? This is for a single observation. Of course, but we wanna like reduce, the error for every single observation. So that's why we have this idea here. So this is the residual, same as the residual. Now, why you see these weird symbols like theta and x? That's because we're just like plugging in the linear regression here because this is my y hat. That's the prediction. So this difference again is the error. Now, why we cannot just minimize the sum of the errors? The problem is like some of them will be positive, others will be negative. So if we add them up, then maybe it will be close to zero if it's symmetric. We have a lot of positive and negative values, so it's not a good idea just to add them up. So that's why we're using here square, and this is the famous mean square error. So we compute the individual residuals, we square them, and we add them up, and we find the average. M here is the number of observations, right? The number of values, like the number of points that we're visualizing here. So the mean square error, it's just our objective. We want to minimize the mean square error. So the whole purpose here is to compute these parameters, the parameters of my model. Typically, in a linear regression setting, we will call these thetas as beta. like beta 0, the intercept, beta 1 for x1, right? So these are the names of the symbol that we typically use for linear regression. But in general, yeah, it's just theta. This is a parameter. It's the same idea, same concept here. Okay, so the nice thing about the linear regression is that it has a closed form solution. This means that we can solve it, we can find the parameters by just solving this equation that is here. So what is that? So imagine that you have your data. You know, we have a table, right? Y, x1, x2, up to, let me use the same notation, xn. And we have m observations here, right? Like different rows. So this is our table with information. This is our data set. So we need to load this information, before training. So what you see as X here, like uppercase X, that will be the matrix of the independent variables. That's X. And this vector Y is just the dependent variable. So this is with the real data. So when you see here the xt, that's the transpose of the X matrix. And then you have the multiplication with X, and this minus 1, it means the inverse, right? The matrix inverse of this operation. So this is just linear algebra. So again, in general, if your problem is small or even like medium size, we can use the normal equation, right? And you will get the solution, the optimal solution. But the problem is when the number of observation increases a lot, like when you have like hundreds of thousands or even millions of observations, then it will take a lot of time, right, to solve this system of equations. Now, that's not the only issue. Also, this works because this is linear, right? A linear relationship. But in some cases, when there are non-linear relationships, then we won't be able to use the normal equation. So there are other alternatives. So this is when we start using the gradient descent algorithm. This one, it's a general optimization algorithm to solve a problem, to like minimize an objective function. So it might work in large data sets. It has like different variants, the gradient descent, which we will discuss in the next slide. You can adapt it, in different settings, large scale learning, but also if you have, data that is streaming, you're getting online data, or if you have nonlinear behaviors. So it's possible to use this algorithm to fit the parameters to estimate the theta values, right? So let me give you a little bit of intuition about the gradient descent. So this is the function that we want to minimize, right? The error, mean square error, let's say. So the idea is that we begin with a random initial value right here, and there is a learning step. Actually, that's a hyperparameter that we need to tune, and it's going to start jumping. So now this moving from one point to the other is not random, because this algorithm is trying to optimize. So it will like differentiate the mean square error equation. It's going to see the direction in which the function, tends to zero. And when we're talking about the slope of this line. So the idea here is to move the estimations in a direction where we are minimizing the cost function. The cost function in this case will be the error, right? We're trying to minimize the sum square of the errors. Now, the learning step matters because if it's too small, it will take a lot of iterations. Like in this plot here, it will take a lot of iterations to get to the minimum value, right? To the optimal value. But if it's too large, the learning step, then maybe our algorithm is going to diverge, meaning that it won't be able to find the minimum value or the optimal value, right? So we need to find a balance, right? We need to compute the learning step to get, our good solution or an optimal solution within a reasonable time. Because here there are two key parameters, the learning step and the number of iterations. Now, a more challenging thing is when we have a nonlinear function, like this one, right here. So it is possible that our gradient descent algorithm is going to get stuck in a local minimum, right? Or maybe in a plateau here, and it won't be able to reach the global minimum. So there are some strategies, right, to avoid this, but sometimes it's just not possible to get to the optimal, especially when you have nonlinear behaviors. It's not that simple as the case where we have like a convex function, which it is going to be easier in that case to compute the parameters in order to minimize a cost function. So let's see some of the variants. Let's mention three different variants for the gradient descent. So we have the batch gradient descent. This one is going to use the complete data set at each update. So in every single iteration, it computes, parameters. It has to differentiate. It evaluates the cost function, right? So the problem with the batch gradient is that it's using the full data set. So if you have a lot of observations, then it's going to be slow. That's why then you have the stochastic gradient descent. This one, it uses only one sample at a time. I mean, just using a single row in your dataset at a time. So the nice part of the stochastic gradient descent is that it's going to be faster, right? Because it only processes a single observation per iteration. But the problem is it has a lot of uncertainty and variability. Sometimes the cost function will go up, sometimes it will go down, right? So there is a lot of uncertainty in whether it will reach the optimum value, the global optimum value. Then there is like in some middle ground, we have the mini batch gradient descent, which is not using the full data set, but it's not using a single observation. So it takes subsets, right? So this is a more like standard strategy in terms of speed and also in terms of consistency while trying to find a good solution. Okay, there are other, let's say, ways to handle nonlinearities. So for example, here we have these observations, this y and x. But you can see clearly that a linear regression model won't be able to fit this line, right? We're not getting the pattern here. If we check if we plot the residuals, you will get like a U form or, like upside down U. So it's not independent, the residuals. So the linear model is not a good idea here for this nonlinear equation. It's more like quadratic. So we need to find a better model, right, to capture the pattern in these observations. Now, the nice thing about the polynomial regression, which we're going to introduce now, is that it is still linear. It is still linear. So let's say that we're trying to model first with, my first model was like y hat equal to slope plus b1x1. That's not a good model, right? But we can try a second one using polynomial regression, which is going to be beta 0 plus beta 1x1, and we add here a quadratic term, so b2. I'm sorry, this is x1. I don't know why I said x2. This is x1. There's only one feature here, so x1 squared. So this is our second model. So maybe you're asking yourself why this is considered still linear if there is a quadratic term here. So the trick here is that we are going to increase the number of the dimensionality. So instead of sticking to a single feature, we can just use like a new variable, an additional variable. So we get rid of the square. So that will be like y hat is going to be equal to beta 0. This is what's happening internally. Beta 1 times x1 plus beta 2 x2. So we're increasing here another dimension into our problem. So in a one dimension, this is non-linear, but when we expand our features, then this is linear. Of course, to compute x2 is going to be x1 squared. So imagine you have your original data with y and x1, right? So here I compute an additional x2, which is going to be x1 squared. And I train the model with this information, right? With x1 squared as x2. So this is linear, x1 and x2. In the polynomial regression, You gotta be careful because the number of features that you are creating, it will increase dramatically with the degree of the polynomial that you are using. So for example, in this one, there is only one variable, so we're just adding the same variable square. But when you have multiple variables, let's say that you have x1, x2, that's different. If you have x1 and x2, let me show it to you real quick. So this is beta 1 times x1 plus beta 2 times x2. Now, if I increase to like a second degree, the degree of the polynomial here, then it's gonna be like, okay, the linear terms, beta 0 plus beta 1 x1. So it's like same thing that we have, plus now we need to add the quadratic terms, right? Because the 2 degrees. So that will be beta 3 x1 squared plus beta 4 x2 squared. And that's not it. We also here need to include the interactions between the variables. So that will be like beta 5 x1 x2. So you gotta be careful here with the complexity of the model, because of course when you increase the degrees you will get a better fit, but then that's gonna increase the complexity of your model, and that might lead to overfitting, which we will discuss in this video. Okay, but again, sometimes the polynomial regression is very useful, because the nice thing is still you can solve this with the normal equation, which is a closed solution, because we can approximate to a linear problem. Okay, so let's see a little bit more about learning curves. So they show the model performance. Let me show you this example here. We have the points are the original observations, right? Same problem as in the previous slide, but we're fitting in different ways. So we have a model with degree 1, so that's a linear regression. It's just a straight line, right? It's not a good fit. We have a 2 degrees, right? Like this quadratic model, it has a better fit. It's capturing the pattern, right? But then here we have something very extreme, like 300 degrees. And now you see that that model is almost like picking every single point. It's trying to pick like, all points here as much as it can. So maybe when you measure the error in the training set, it will be very small for the 300 degrees polynomial, right? But the problem is that that model is not good to generalize. It's going to overfit your data, meaning that when you test it in new data, the performance is going to drop. So let's see the learning curve, because it helps us to see if we are underfitting or overfitting, or if we are in the right spot. So in the first one, so here blue is testing error, red training error. So in this one, the error is in the y-axis, and number of instances, this is like number of observations that we're using. You can see this as a percentage too, like, okay, we're using here 10% of the training set, 20, 30, 40, 50, 60, right? Like how many observations we're using from the training set. So as we increase the instances, then, okay, we have the error is increasing. And in the validation set, is decreasing, but the error here, if you compare it with the others, it's high, right? It's high. The error here is high. It's higher compared to the other plots. So here we have what we call high bias. High bias means we are underfitting our model. It's like our model is not making a good estimation. It's far. This is like the straight line trying to match or to fit the quadratic behavior of the original data in our example. Let's see the other extreme performance. So in this one, look at the training set. This is the case of the 300 degrees polynomial regression. Look at the performance. The error is very low, extremely low, right, in the training set. But in the validation or in testing, the error is not that big, it's not that small. Actually, there is a huge gap between these two. So that means that the model is not generalizing properly. And that's not good because we don't want to create a model just to fit the training data. We want to create a model to be able to generalize and to be able to predict when it gets new data. So this is what we call overfitting. When you have a huge gap between the training error and the testing or validation error. That will be, again, this is overfitting. So this is the ideal case, right? Where you have, like, okay, the error is smaller than the first scenario, but you see that the gap is closing, right? The gap is closing between the training error and the testing error. So this is the behavior that we're trying to see, like small error, and also that the distance between these two are not that big. Because they won't be exactly the same. That's difficult, and because there is uncertainty in the process. But again, this is the ideal behavior. Okay, so even though I mentioned this, the first concept in the previous slide, let's clarify a little bit more what is bias. So the bias is just a systematic error that is caused by the model's assumption, assuming that the model is linear when it's not. So that's underfitting the model, right? So high bias means underfitting the model. And what is underfitting the model? Pretty much it means that our model to predict the variable is not identifying correctly the patterns in the data. Right? It's not a good model, right? It's not a good model. We need to increase a little bit more the complexity if we have high bias. On the other hand, we have variance. So variance, it refers to the fluctuations in the training set. So when you have high variance, that's an overfitting. So in the previous slide, here we have high variance. You see that the model is trying to capture every single point. So that's high variance. It's not getting the pattern. It's just trying to go, to reach every single point. So it's capturing the variance instead of capturing the pattern. So in general, we will have these two errors. Actually, we will have three errors: bias, variance, and there is like a normal or natural error that is impossible to reduce. It's just the uncertainty that we have in life. So the trade-off is if you try to improve one of these, you will affect the other one. If I try to reduce bias, I will affect the variance. So let me show it to you. This is in different situations. So in regression, similar as the previous example. So here we're underfitting, right? So here we have high bias. In this example, high bias. This linear regression model is not capturing the pattern here. Overfitting is we're going after every single observation. Then here we're reducing the bias, but we have high variance, right? So the idea is to get it just right, like in the middle. So here is the training error is lower than the test error, and we're not like pursuing every single point. We're trying to generalize here. We're trying to generalize the relationship between the variables. So that's for regression. You can see the same thing for classification, for deep learning. There are some possible solutions, of course. In the case of underfitting, so you need to increase the complexity of the model. Maybe if you're using a polynomial regression, you can increase a little bit the degree, or you can train a different algorithm. That's another possibility. We can add more future, maybe future engineering here, and of course you can train longer to see if it improves the performance. If we have the overfitting issue, then there are some options. We can get more data, and of course we can perform some regularization. So what is regularization? Because when you have overfitting, it means that the complexity maybe of your model is too high. You need to decrease it a little bit. So we have some techniques for model regularization. So here let's discuss three regression techniques: rich regression, lasso regression, and elastic net. So in the three algorithms, we have a cost function. So remember, originally we were trying to minimize the mean square error, right? We want to estimate the model parameters to minimize the mean square error because we want to have a good model, right? So we have the mean square error in the three methods. So now the change is in the second part of the equation. So what these methods are doing in the rich regression is penalizing the model for the weights of the parameter, the values of the parameters. So if the idea here is if, let's say, a variable is included, because it matters. It has to be important to reduce the error. But if it's not that relevant, then this value is going to tend to be equal to 0. So it's going to remove that variable in order to decrease the complexity of the model. So here we have the value of the parameters squared, the weights of the parameters squared. In the lasso regression, instead of the square, it uses the absolute value, but the idea is pretty much the same idea, to reduce the weights, the model weights. And the ElasticNet combines these two. It has two expressions, but if you check them, they are exactly the same. So here we have the lasso regression expression, right? The absolute value of the thetas, of the parameters, and the other expression here is just the parameter values squared. So ElasticNet is just a combination of rich regression and lasso regression. And the idea of these three algorithms is just to reduce the complexity of the model that you're trying to find. So when you regularize, you are reducing the likelihood of overfitting. Another techniques, the early stopping. This one is very useful, especially for when you're training neural networks. This one is very common. So the idea here, when you have an iterative learning algorithm such as the gradient descent, is to stop the training once the validation error has reached the minimum. So here we have the epochs. They are similar but not exactly the same as the iteration, but they are related to the number of iterations. So as we're increasing the number of iterations, then the gap between the training and the validation set is reducing. But then if you keep going, it is possible that the gap is going to increase, right? So here the early stopping means, hey, you have to stop here, right here, at this epoch, because this is where you're getting the best performance in your validation set. So this is a very common tool for neural networks to identify when to stop the training with the early stopping. All right. So in this presentation, we discussed different training methods, like the normal equation, which is a closed form solution, gradient descent, which is very flexible. It's not just for machine learning. It's in different settings. You can use gradient descent when you're trying to optimize. Regularization, which helps us to reduce overfitting, right? We covered like different techniques, lasso, rich, and also the ElasticNet. So remember that the purpose here is not just to find model parameters. Our idea is to generalize our models. And when we mention the word generalize, it means that the model that we're training is going to be good with new data. Because that's the whole purpose of this, that when we deploy the model in real life, it's going to make good predictions. So we will be confident that will happen if our model is generalizing, means good predictions with new data, in new data. The gradient descent algorithm, it's good when you have when we're scaling to with a lot of information, with more features, then it's going to be better than the closed form, because it becomes impractical when we have a lot of data in big data settings. So regularization helps us to reduce overfitting, right? So introduces bias in exchange for reducing the variance. That's pretty much the idea. This trade-off, it's always present in machine learning. Like all models discussion is very common when you're training algorithms or when you're training models, the bias and variance. So we need to find the sweet spot, right? Where we have, like low bias and low variance, like balance, good balance of these two. Because typically, especially for the new learners, when someone is new in machine learning, your focus is like, the bias. I mean, you will try to get good models with high complexity when you are, like tuning every single parameter. But the problem is that maybe you're affecting the generalization of the model when you increase the variance. So it's important to keep the balance here. All right, I'm going to stop the video for now. I'll see you in the next lecture.